Welcome to day 6 of my honest interview preparation. Today we will solve the maximum subarray sum problem and understand how interviewers expect us to optimize it. Let's start.
The problem is we are given an array of integers and we need to find the maximum sum of a contiguous subarray. Contiguous means the elements must stay together. Let's use this small example. In this example, the subarrays are minus 2, minus 2, 3, minus 2, 3, minus 1, and minus 2, 3, minus 1, 4. If we take minus 2, minus 1, this is not a contiguous subarray because we left out 3, so the elements should be adjacent to each other. The most straightforward approach is brute force. We try all the possible subarrays, calculate their sums, and keep track of the maximum. Let's use this example again. First, we will find all the subarrays. So from minus 2, it will fix minus 2 first, and then the possible subarrays would be minus 2, minus 2, 3, minus 2, 3, minus 1, and minus 2, 3, minus 1, 4. It will then fix the next element, that is 3, and take out all the possible subarrays starting from 3. So the subarrays would be 3, minus 1, and 4, and so forth. Here we are using two loops, one to fix the element from which we are starting the subarray, and second to iterate through the loop to create all the possible subarrays starting from the fixed element. This works fine, but the time complexity is O of n square, which is usually not acceptable. It fails because as input grows, this quickly becomes impractical. But can we do better? In interviews, once you give a brute force solution, the next question is almost always, can we optimize this? This problem becomes easy once you understand one key idea. If the current running sum becomes negative, it will never help any future subarray. Adding a negative sum only reduces the total. So instead of carrying it forward, we drop it. Kadane's algorithm is based on dropping a negative running sum. Let's walk through this example once. We start with the first element minus 2, initialize the current sum with the first element, that is minus 2. The maximum sum as minus 2 as well. Now this makes the running sum negative, so we drop it and update the current sum to 0. And the maximum sum will be maximizing current sum and the maximum sum, that is 0 as well. Now at 3, starting fresh gives us the current sum 3. And the maximum sum will be maximum of 0 and 3, which is 3. Now at minus 1, the current sum will be current sum plus the current element, that is 2. The maximum sum will be 3 again. Finally, adding 4 further increases the sum to 6, and the maximum sum will be maximum of 3 and 6, 6. This becomes the maximum subarray sum. Now that the approach is clear, let's walk through the implementation. This function returns the maximum sum of any contiguous subarray. I initialize the running sum with the first element so that the algorithm works correctly even if all the numbers are negative. I also initialize the maximum sum with the first element to ensure we always return a valid subarray sum. I start iterating from the second element because the first element is already accounted for here. At each step, I extend the current subarray by adding the current element. After extending the subarray, I check if this gives a better maximum sum than what I have seen so far. If the running sum becomes negative, I reset it to 0 because carrying a negative sum forward will only reduce the sum of any future subarray. Finally, I return the maximum subarray sum here. Here the key idea is resetting the sum to 0. This means I am discarding the current subarray entirely and preparing to start a new subarray from the next element. If I reset this to the first element instead of 0, I would be incorrectly reusing elements from the beginning, which breaks the continuous subarray logic. Now let's run this code. In the first case, the maximum subarray sum is 6. It has considered these three elements. In the second case, where all the elements are negative, the maximum sum is minus 2. And this explains why we are using first element as the current sum and not 0. Because if we had used 0 instead of the first element, then 0 would have been the maximum element throughout and the output would be incorrect. It would be 0 instead of -2 here. As we are iterating the array once, this reduces the time complexity from O of n square to O of n. And since we are using only a few variables, the space complexity is O of 1. This reasoning matters more than memorizing Kadane's algorithm. Interviewers are not testing whether you remember Kadane's algorithm, they are testing whether you can recognize that a negative sum should be dropped. This is pattern recognition, not memorization.
So remember, solving the problem is just step 1. The key step here is not memorizing Kadane's algorithm, but understanding why we drop a negative running sum. If you can explain that clearly, interviews become much easier. See you in the next one.